Hello and welcome back to another video. In this video, we're going to solve the remaining chapters, which are magnetism, waves and light, and some nuclear and space physics, and then we'll solve some questions for paper 2. Let's begin. Now we'll start with magnetism. Okay, so one of the most important concepts in magnetism is induced EMF. What is induced EMF? Basically, it's a way in which we can create electricity using magnets. Okay, so here we have two magnets, and they have like all magnets have a magnetic field between them, which goes from the north pole to the south pole. Then there is a conductor in between them. Now whenever you take this conductor and move it up or down, and basically you are cutting through these field lines, you are creating an induced EMF. Then you will see that the galvanometer will show a reading because an EMF or voltage is induced in the wire. So basically EMF is induced at a rate at which a conductor cuts the magnetic field lines, or if it cuts a lot of magnetic field lines, the induced EMF will be more. Therefore, if you want to increase the induced EMF, you have to increase the speed of motion of magnet or coil. So you can either have a conductor, you can even have a coil. For example, in solenoids, you have a coil. Or if you move your magnets very quickly, that is also going to increase the EMF. It also depends the strength of magnet, not the coil, because if the magnet is stronger, it's going to have more field lines per unit area, and that means more lines are going to be cut. Now, if you see an example of AC generator, in an AC generator, alternating EMF is induced. But for IGCSE, you need to know the diagram, the labeling, and the working of an AC generator. Basically, in simple terms, an AC generator has a coil of wire, and this coil of wire rotates in a magnetic field. As the coil rotates, it cuts through the magnetic field and an EMF is induced. So in AC generators, electricity is produced by mechanical energy. Mechanical energy, or the energy because of movement, is converted into electrical energy. Now in DC motors, however, the opposite happens. So in DC motors, you have a permanent magnet that has electromagnetic field around it from north to south pole, and you also have a conductor that has current flowing through it. Whenever there's a conductor that has some current flowing through it, for example, if the current is going down, it also has a magnetic field around it, something like this. And if you don't want to know the direction of the magnetic field, thumb points towards the direction of current, that is thumb, and where your fingers roll, which is going to be here, that shows the direction of the field. In DC motors, we have a permanent magnet which has its own magnetic field, and then there is also a coil, or basically an armature, which carries current. When you turn on the current and current flows through the conductor, which is already in a magnetic field, the magnetic field lines of the wire are going to cut through the magnetic field lines of the strong magnet, of the permanent magnet, and that is going to cause a force on the wire. So this wire is going to move up or down. The electrical energy in the motor is converted into motion or mechanical energy. Okay, Fleming's right hand rule is always used for generators or whenever there is an induced EMF. If you have two of these quantities, you can determine the third quantity. So your thumb represents the motion of the conductor, where the conductor is being moved. Your first finger represents the direction of magnetic field, always from north pole to south pole, and the second finger represents the induced current. This is conventional current, so it shows the direction from the positive to negative. On the other hand, Fleming's left hand rule is also known as motor rule. This is used when motion is created. Okay, the thumb represents the thrust. This is basically the motion or the force experienced by the coil or conductor. The first finger represents the direction of magnetic field from north to south pole, and the second finger represents the current, the flow of current from positive to negative. Now, the application of Fleming's left-hand rule is in DC motors, and it's also used in charge. For example, if you have a charged particle which is traveling through a magnetic field. Plus represents that the magnetic field is going into the paper. Dots represent that magnetic field is going out of the paper. And then you have a charged particle, could be a proton, could be an electron, and an electron that's going in. So you can apply Fleming's left-hand rule to identify where this electron is going to move. Now another very important concept is for transformer. Transformer is an electrical device in which is used to change the value of alternating voltage in from your source to either a greater value or to a smaller value. For example, if your input voltage was 1000 volts, you can increase it to 2000 volts, so that is called a step up transformer, or you can reduce it to maybe 5 volts, that is a step down transformer. So this is what a transformer looks like. It has a primary coil and a secondary coil and a soft iron core in between it. So whenever the current is switched on in the primary or off, or the current is changed, a voltage is induced in the neighboring coil in the second one. Basically, the most important concept is that field lines are cut. V1 or V in the primary coil divided by voltage in the secondary coil equals to N1, the number of turns of coils in the primary, to the number of turns of coils in the secondary. An easy way to identify whether this is a step up or step down a transformer is to look at the number of coils. If the secondary coil has a greater number of turns of coil, that means it's a step up. If the secondary one has less number of coils, it's a step down transformer. One more equation is that power in the primary or power in the input equals to power out. So remember, power equals to IV. So I primary multiplied by voltage primary equals to I of secondary and voltage of secondary. You can also write this as IP divided by IS equals to VS divided by VP. You can even equate this equation with this equation. So here is V secondary over V primary, NS and NP. Next, why do we need a transformer? So basically we have a powerhouse. A powerhouse is used to provide electricity to people's homes. At homes, we don't need very high voltage. We need low voltage. But the problem is if we have low voltage, the current would be high. And if the current is high, a lot of power is lost in cables. If you look at this definition, power lost equals to I squared R. Therefore, in cables, we use very high voltage and low current. So what are some advantages of using high voltage in cables? Less power is lost in cables, and secondly, because the current is low, we can use wires that have a small cross-sectional area. So this is going to be cheaper and much easier to handle. A metal rod XY is placed in a magnetic field. So this is the metal rod and this is the magnetic field. Okay, so that is perpendicular to the field as shown. In which direction is the rod moved so that there is an induced current from Y to X? Okay, so there is induced current, therefore we need to use Fleming's right hand rule. To do this, align your first finger with the direction of magnetic field, or align your second finger with the direction of current upwards, and then you will see the motion is out of the paper towards you, towards the observer. So it's going to be D. Next, okay, so this diagram shows the basic electric motor. All right, what are the name of the features? So remember, X is the coil. This is turned in between the magnetic field, so it's B. These brushes are used to maintain the contact between this circuit and this commutator. Brushes are made up of carbon. Z, which are commutator, are used to reverse the direction of current after every half turn in this DC motor. Two transformers, P and Q, each have 2000 turns on their primary coils and 1000 turns on their secondary coil. Both transformers are 100% efficient. The secondary of transformer P is connected to the primary of transformer Q. Q provides motor with a current of 0.2 ampere. What is the current being supplied to the primary transformer P? Alright, let's draw a diagram to understand what's going on. Okay, they told us that Q provides a motor with current to 0.2 ampere. That means this is the current over here, 0.2 amperes. Now you need to find the current here. And they said P is connected to primary, so this current is going to be same as well. Let's call this X. This is also X. So by finding X, then you can find Y, current that is being supplied to the primary of transformer P. Remember, when you have current and coils, this is not same, like you have P primary here and secondary here. So if you look at this example, we need to find IP. So IP equals to IS, which is 0.2 multiplied by 1000 divided by NP, which is 2000, and that is going to be 0.1 ampere. So that means x is 0.1 A, and so is this. Now you need to apply this equation between them and find I primary again, which is y. So IP equals to I of secondary 0.1 multiplied by 1000 divided by 2000, and that is going to be 0.05 amperes. So it's D. The diagram shows part of the magnetic field around a strong magnet. In which position does the magnetic pole experiences the strongest force? So it experiences the strongest force where the magnetic field is the strongest, and magnetic field is going to be strongest where magnetic field lines are very close to each other. So that is going to be A. Right now let's discuss about waves. There are two types of waves. Either you can have a transverse wave or you can have a longitudinal wave. In a transverse wave, the direction of vibration is perpendicular to the direction of propagation or to the movement of the wave. Include all the electromagnetic radiation, including light, also the waves in water, the seismic S waves. In longitudinal waves, the direction of vibration is parallel to the direction of wave propagation. So some examples of longitudinal waves are sound waves and seismic primary waves. So this is an example of a transverse wave. You have a crest that goes up and you have a trough that goes down. But in longitudinal waves, you have regions that particles are very close. This region is called as compression. And then you have regions where particles are far from each other. That is called the region of rarefaction. And then again you have a compression. The distance between two consecutive compressions or rarefaction is the wavelength. Okay, let's look at this wave in detail. Peak is a crest and so is this. On the other hand, this one is the dip is called a trough. Amplitude is the region from undisturbed position to the maximum height. That's amplitude. Amplitude can also be from here to the minimum. A wavelength, which has this symbol, is the distance between two consecutive points on a wave. So it could be from the starting of the crest to the next crest. Okay, it can also be from the top, from a peak to peak. That's also wavelength. It can also be from trough to the from peak of the trough to another trough. So one crest and one trough makes up a complete wave, and this is the wavelength is measured in meters. Now we have two more equations. First is V equals to F lambda. V represents the wave speed. It is frequency multiplied by wavelength. So frequency is basically number of complete waves. Frequency is basically how many waves are produced in 1 second. Its unit is in hertz. Okay. Time period, on the other hand, is the time taken to complete one cycle of wave. Okay, time period is measured in seconds. Now if you have a wave and you're asked to draw a wave that is louder than the original wave, so all you have to do is increase the amplitude. If you see that this light purple represents the original wave, we just increase the amplitude to create a wave that has a louder sound. On the other hand, if you're asked to draw a wave which has higher pitch, you have to increase the frequency. The amplitude does not change. Waves can undergo reflection, diffraction, and refraction. So when reflection occurs, the speed of wave, the frequency, and the wavelength of the wave remain same. The only change that happens is direction. So something like this, and direction has reversed. On the other hand, diffraction is when the wave passes through a hole. Then the speed, frequency, and wavelength remain same, only the shape of the wave changes. And then finally you have refraction, when the wave travels from one medium to another, so speed changes, wavelength changes. However, the frequency remains same. As the wave moves from rarer to denser medium, it becomes closer to normal. Why? Because the speed has reduced and the wave becomes closer to the normal. However, if it goes in the other direction from denser to rarer, for example from glass to air, it moves away from normal. So looking at where the wave is moving, you can identify which medium is denser and which medium is rarer. Snell's law is used to find a refractive index. What is a refractive index? Refractive index, or N, measures how much light is bent when it moves from one medium into another. So the formula for refractive index is speed in air divided by speed in medium. For example, this diagram shows that the light is moving from air to another medium. This bend can be measured by the refractive index. Every material has its own refractive index. Then you can also find n by sine I, the incident angle, over the refractive angle sine I over sine r. And n can also be found by the critical angle. Critical angle is the incident angle when a light is moving in a denser material, and if it doesn't move into the rare material, instead it goes through the surface. The angle of refraction is 90 degrees. That angle is critical angle, so the formula is n equals 1 over sine c. If the angle of incidence becomes greater than the critical angle, we have total internal reflection. So the light does not move outside, it does not refract, rather all of the light stays inside the medium and goes on. One application of this is in optical fibers. So lenses can be of two types. We can either have converging lens or diverging lens. In converging lens, the light waves are going to converge at one point. However, in diverging, they are going to diverge. So there are some rules. So if your object is, for example, beyond 2f, somewhere here, for example, the image will be real, but the size will be smaller, it's going to be inverted, and it's going to be closer to the lens compared to the object. If your image is between f and 2f, the image is going to be real, bigger, inverted, but further away. If it is on 2f over here, the image is going to be real, same size, inverted, but at equal distance as that of the object. If the image is between lens and the focal length, that means if the object is here and then you draw the diagram, you will see that these lines never meet. So you extend these lines backwards and it's going to meet here. So the image is going to be virtual, bigger, upright, it's not inverted, and it's going to be behind the lens. That means here, this is the image. So you will keep your eye here to look at the image. One example of that is for magnifying glass. Water waves are reflected at plane surface. Which property is changed by reflection? Remember, frequency, speed, and wavelength remain same. The medium is same. Only the direction of propagation changes. Next, a light ray is passed through air, glass, and water. At which point does the light speed decreases? Okay, so light speed decreases as it moves from a rarer to a denser medium. So it's going to come closer to the medium. So you can see the angle of refraction is smaller, it's 28. So, and also in water it's smaller. So at point W and point Y, the speed decreases. Plane water waves approach a narrow gap in a barrier. Which diagram shows the diffraction pattern that would occur? You need to have circular waves, so it's going to be C. Why not B? If you see, the wavelength before and after the diffraction should be same. So this one represents the wavelength, and if you notice, it increased a lot. So the size should be same, which is same in C. A ray of light enters a transparent plastic wedge, this one, from air and is incident on the lower surface at a critical angle as shown. So here you can see it passes through the wedge and it has 90 degrees and it is perpendicular. The angle of incidence is I, the angle of refraction is R, and critical angle is C. In which diagram are the angles labeled correctly? Okay, so this is the critical angle and this is the incident angle. Okay, so these angles are between the waves and the normal. So if you look at B, that's correct. Okay, now we have a lens diagram. An object is placed 20 centimeters here from a thin converging lens. The scale diagram shows how the lens form a real inverted image. Which row gives the focal length of the lens and the distance from the image from the lens and distance of the image from the lens? So what is the distance of the image from the lens? Okay, it says one block is 5 centimeter. So this is 5 centimeter. So it's going to be A. Radio waves are electromagnetic waves. What is the wavelength of a radio wave of frequency of 2 times 10 power 5 Hz? Remember, V equals to F lambda. So lambda is going to be V. Remember, it's electromagnetic wave. So the speed is going to be the same as speed of light. 3 times 10 power 8 divided by 2 times 10 power 5 hertz. If you calculate it, you will get 1500 meters. A candle flame is placed in the front of a loudspeaker. So you have a loudspeaker and a candle flame. The loudspeaker produces a sound wave that causes air particles to vibrate. The vibrating air particles make the candle flame vibrate in the same direction as the air particles. Which row shows the direction of vibration of the candle flame and the nature of sound waves? Remember, sound waves are longitudinal, so the direction of vibration is the same as the direction of wave propagation. So it's going to be either C or D. These are parallel. And remember, sound waves are longitudinal, so it's going to be C. Now let's move on to nuclear physics. So some important concepts in nuclear physics are these, which are explained here. During radioactive decay, alpha, beta, or gamma are released. They have their own properties, their own charges, and so on. So this table summarizes that. Alpha particle is basically a heavy particle. This is the symbol, and it has the same proton and neutron number as helium nucleus. 2 protons and 2 neutrons. It is a positively charged particle because it has more number of protons, so it's going to be +2. The penetration is low, but ionization is high. Okay, remember, penetration and ionization are opposite. This is low and high, but for gamma it's the opposite. We'll go through it one by one. Alpha particles have very high ionization and very low penetration, basically because they have a large mass and they have a charge of +2, and it interacts with the particle and it rapidly loses its energy. Therefore, because it ionizes, it has very low penetration. What about beta? Beta is basically a high energy electron. These are negatively charged, and this is what beta looks like, and it has only one electron. It has no protons, no neutrons. The penetration is medium, and so is ionization, blocked by materials like a thin aluminum sheet. And finally, we have gamma. Gamma is not a particle. Gamma is basically a radiation, okay? It's an electromagnetic radiation. This is the symbol of that. Its charge is 0. It has very high penetration but very low penetration. And if you want to block it, you need to block the source by thick lead or concrete because it has very high penetration. Okay, now let's look at nuclear equations for radioactive decay. Let's say you have a uranium atom which has the mass of 238 and the proton number of 92, and it undergoes alpha decay. So you can say something like this: helium 42, or an alpha particle. So you have 4 and 2 here. Therefore, you're going to subtract this by 4 and this by 2. Now this is balanced. 234 plus 4 is 238 and 90 plus 2 is 92. Now let's say you have iodine with the mass of 131 and protons and 53 protons. It undergoes beta decay. So beta particle is released. Remember, beta particle is just an electron, right? So it's 0 and -1. Xe xenon. You don't have to learn the names of new elements. All you have to know is give the new numbers, something like that. You can be asked to identify the new particle. Okay. You can see that the mass number did not decrease at all. It's 0. So you can write this as 131. But there's an increase, but you have -1 here. So you will write 53 plus 1. You will write 54. Why? Because 54 plus -1 is going to be 53. So this is a beta decay. Now let's look at a gamma decay. Remember, gamma is not a particle. Gamma is a ray. So we have uranium 238 and 92. Gamma ray has no mass or charge, so it's 0, 0. For this equation, it also released an alpha particle, so 4 and 2 for helium. So what are going to be the new numbers for mass and the proton number? This is going to be 90 because 90 plus 2 is going to be 92, and this is going to be 234. And this is how it's balanced. Now another concept in nuclear physics is half-life. Radioactive atoms have unstable nuclei which constantly decay into atoms of different element, and they emit alpha or beta particles. So half-life is the time taken for half of the nuclei to decay. It can be as small as a few milliseconds, and it could be as long as hundreds of thousands of years. Now, the unit for half-life is becquerel. Example, let's say this was 200, and the time taken for it to reduce by half, which is 100, is your half-life. Half of nuclei have decayed, so at 100 you will find the corresponding time. Let's say this is 50 years, so that is the half-life. Now if you find for 50, and if you find the corresponding time, that is also going to be 50 years. So this is the half-life for that particular element. Alpha particles are directed at metal foil. Most of the particles pass through the foil with little change in direction. Okay, a small proportion of particles, however, are scattered back through the large angles. So this is basically the Rutherford experiment, in which a Rutherford shot alpha particles on a metal foil. And then he found out that since most of the particles pass through the foil, they pass straight through the foil with little change in direction. It indicates that most of the particles are empty. They have a lot of empty space in between. So most of it is empty, but a small proportion of particles were scattered back through the large angles. So since only a small proportion of the particles were scattered back, the mass is concentrated in the center, which is in the nucleus. This indicates that there is a tiny heavy center in the center of the atom, which is called the nucleus. And he also found out that the nucleus is positively charged. Why? Because it actually repelled away, they're scattered back through large angles. It repels away the positive alpha particles. So let's look at the options. It consists of a charged center, much smaller than the size of atom. That's correct. With little of the mass. No, it has most of the mass, so it's not A. It consists of a negative charge. No, it has a positive charge, because that's why it's repelling and the particles are scattered back, so it's not B. It consists of a charged center, much smaller than the size of atom. That's right. But with most of the mass of atom. That's correct. Most of the mass is just concentrated in the center. It consists of a positive charge of the size of the atom containing small negative charges scattered through it. No, it does not explain that. Which statement correctly compares the properties of alpha particles and beta particles? Alpha particles are less penetrating than beta particles. That's correct. So we can eliminate C and D because it's not more penetrating. Then, because alpha particles are less ionizing, no, they are more ionizing. Remember, whenever there is more ionization, there is less penetration. So 35 is B. Which statement about alpha decay is correct? The nucleus loses electrons. No, there is no change of electrons, and the electrons are not in the nucleus anyways. B, the nucleus changes to that of a different element. Yeah, that's correct, because the proton number changes. Whenever there's a change in proton number, the element changes. So 36 is B. Next, the nucleus does not decay until after one half-life. No, that's not correct. D, after two half-lives, alpha decay always stop. No, that's alpha decay does not depend on the half-lives. Now, an explosion in a nuclear reactor spreads the isotope cesium-137 across a large area. After 90 years have passed, the quantity of cesium present is 12.5% of its original level. What is the half-life of cesium-137? So initially it was 100%. After one half-life, it reduced to 50%. After another half-life, it reduced to 25%, because you're just basically dividing them by 2, okay? And after another half-life, it's 12.5%. So it says all of these. So to reduce from 100% to 12.5%, it took us 90 years. So that means 1, 2, 3 half-lives have occurred. Therefore, you're going to divide 90 divided by 3, and you will get 30 years. So the answer is C. So it was 0. After 30 years, it was 50%. After another 30 years, which is 60 years, it was 25%. And then plus more 30 years, which is 90 years, you get 12.5%. So it's C. Now for space physics, I am focusing on the equations, okay? or the formulas. Orbital speed is 2 pi orbital radius divided by time period. Basically, if you have, this is the orbit, and to find out the speed of a planet to move around this orbit, you have to divide 2 pi of the orbital radius from the center to the by the time period. Time period is basically the time taken for a moon or a satellite or something to move around the complete orbit. That is orbital speed. In terms of formulas, it's going to be v equals to 2 pi r divided by time period. You may also have to use this equation, speed equals to distance divided by time. For example, if asked to find the time taken for sunlight to reach Earth, so you have to find the distance between the sun and the Earth. It can also be the orbital radius, and then you have to the speed is going to be speed of light, and then you can easily find the time. Now, 1 light year equals to 9.5 times 10 power 15 meters. So, for example, in your question, if they say that this object or this planet travels for 15 light years, so you have to multiply 15 with this number. Now, what is Hubble's constant? Hubble's constant equals to recession velocity divided by distance traveled. Recession velocity is the speed at which a galaxy moves away from the Earth, and the distance is between the distance of the Earth and the galaxy. The current estimate of Hubble's constant as per today is 2.2 times 10 power negative 18 per second. Now, if you find the reciprocal of Hubble's constant, this gives you the age of universe. This also tells us that this also proves that universe or Earth expanded from a single point, and it's continuously expanding away from us. If you look at this graph here, when you have distance on the x-axis and on the y-axis you have recession velocity, you can find the gradient. Gradient is always y over x, so recession velocity divided by distance is going to give you the gradient of Hubble's constant, HO. Now let's solve some questions. Okay, which type of object rotates around the sun with an elliptical orbit? So elliptical orbit is basically an oval shaped orbit. Planet, yes. For example, Earth, it rotates around the sun with an elliptical. Galaxies don't rotate around the sun in an elliptical orbit, so it's not B. Red giant, individual red giants do not have orbits, but they have some other clusters. So it's obvious it's not C as well. And moon does have an elliptical path, but it moves around the Earth, not around the sun. So it's A. Next, which statement about sun is correct? The nuclear reaction in sun creates mainly radio waves and microwaves. The sun is powered by fission reactions in which hydrogen is converted into helium. No, that's nuclear fusion, not fission, so it's not B. The sun is powered by fission reaction in which lithium is converted into helium. No, a hydrogen is converted into helium. D. The sun is powered by nuclear fission and electromagnetic radiation is produced. That's correct. Finally, the last question. To determine the value of Hubble constant, an astronomer measures the distance of a galaxy of the Earth from the Earth as 2.5 times 10 power 21 kilometers. She also measured the speed of the recession of the galaxy from the Earth as 5.2 times 10 power 3 km per second. From these data, what is the value of Hubble's constant? Remember, the formula for Hubble's constant is going to be recession velocity divided by distance between two objects, between two planets. So recession velocity here is 5.2 multiplied by 10 power 3 km per second, and the distance is 2.5 times 10 power 21. If you calculate this, you will get B, 2.1 times 10 power negative 18 per second.